Again, we are going to see about the Friis formula, which is used to measure the amount of power received by the radio receiver in any transmission line or the link. So the general radio link is shown here, which is having the source, which is represented by this source symbol with the transmitter power of PT, and this source is connected to the load, which is represented by this resistor with the received power of PR. So here this is a transmitting antenna symbol, and similarly this is a receiving antenna symbol. This transmitting antenna having the gain of GT and the received antenna having the gain of GR, and this arrow represents the wireless communication link with the distance of R. Now our purpose is to find the received power by this radio receiver or the load. So here the transmitting antenna gain is GT and the received antenna gain is GR, and the received power is PR. The transmit and receive antennas are separated by a distance R. So here first the power density radiated by the isotropic antenna. If you assume that the transmitting antenna is isotropic antenna, so that antenna radiated power density, which is given by this formula PT by 4 pi R square. Since we have assumed that the antenna is isotropic, we know that the isotropic antenna have equal radiation in all 360 degree. That's why we have considered the entire area of the sphere, that is given by 4 pi R square. So the power density radiated by the in general any arbitrary transmitting antenna, the power density radiated, it is given by this. So here why this GT is not here? So for isotropic antenna GT is equal to 1, that's why there is no GT here. But for any arbitrary antenna, the power density radiated in the free space, that is given by the ratio of GT PT divided by 4 pi R square. So if this power density is incident on the received antenna, so we can have the concept of effective aperture area in order to find the received power. So the received power PR is equal to GT, PT and AE, which is nothing but the effective power through which the antenna capture the radiated energy. So GT, PT, AE divided by 4 pi R square. So by using that formula, we can able to find the final received power. So that is given by this one. So PR is equal to, it is directly proportional to the gain of the transmitting antenna, gain of receiving antenna and the transmitting power divided by the 4 pi R the whole square. So this formula, it is called as Friis radio link formula, which is basically addressing how much power it is received by any radio receiver in wireless communication. Next topic is link budget and link margin. What is the meaning for link budget, sir? So we have different parameters, so different values in Friis formula in order to calculate the received power, right? So the various terms in the Friis power are tabulated or separated in a link budget, where each factors can be individually considered in order to calculate the net effect on the received power. So here when we calculate the received power, we have to see the loss factors also, such as the line loss or the atmospheric attenuation or the polarization mismatch loss. So these factors or these loss factors also we should consider. So one of the term in the link budget is path loss, which represent the free space reduction in the signal strength with the distance between the transmitter and receiver. That path loss in dB, which is given by L naught of dB is equal to 20 log of 4 pi R divided by lambda, right? So here, according to the Friis formula, these are all the different parameters which involved in the calculation of the received power PR, where it is PT is a transmitting power, that is the income actually, that is a transient power, that's why we have represented in a positive. But here the different losses that occurs, like transmit antenna loss as minus LT and the path loss in free space minus L naught, atmospheric attenuation minus LA, received antenna line loss, that is minus LR. So these are all the negative, these are all represented in negative since it is the loss of energy. So that's why it is represented in negative, and the remaining power and the gain factors are represented in positive. So here this is called as link budget. So according to this link budget, the received power, the new formula can be calculated, which is represented in dBm, which is equal to all the positive factors, that is GR, GT and the PT are represented as positive. Remaining loss factors LT, L naught, LA and LR are represented in the negative manner. So here this is the transmitting this is the received power formula according to the link budget. If the transmitted receive antenna is not impedance mismatch, right? So the impedance mismatch will reduce the received power by a factor of 1 minus eta 2, where eta 2 is the reflection coefficient of the receiver. So according to that, if this consideration, the impedance mismatch loss, it is given by L impedance is equal to minus 10 log 1 minus reflection coefficient. So here the impedance mismatch loss is always directly proportional to the amount of impedance mismatch between the transmitter and the receiver. Then what is the meaning for link margin, right? So here link margin, it is in practical telecommunication system, it is usually desirable to have the received power level greater than the minimum acceptable level. That minimum acceptable level, it is called as threshold level, right? So there should be a minimum acceptable level for all sort of wireless communication link. So the above so that is a minimum level above which they generally usually the received power should be have. So this minimum threshold level, it is called as the amount of minimum acceptable level required for quality of service. It is represented in terms of CNR, which is nothing but carrier to noise ratio, or it can also be called as minimum SNR. So it receives it allows the design of design of communication link with received power, which is represented as a link margin, which is given by the difference between the design value of the received power and the minimum threshold value of the received power. Where this is a formula, the link margin, it is measured in dB, that is represented by Lm, that is equal to PR minus PR min. This PR min, it is called as CNR or minimum SNR or minimum acceptable threshold value, and this is the actual received power we should get, right? That is so the actual received power minus the minimum threshold power, which is defined as the link margin. So this is represented in dB. Link margin should be a positive value. The typical range is from 3 to 20 dB. So if the link margin is used for accounting or studying the fading effect, then it is called as fade margin. For example, for satellite link operating at a frequency of 10 gigahertz, the fade margin of 20 dB are more to account the attenuation during the gain losses. This is nothing about the link budget and link margin for wireless communication system. Thank you.